All right. So now we're going to talk about ternary phase diagrams. And what I want to start with is the features of the phase diagrams. We'll talk about some operations we can do to get information about the system, but I want you to become familiar with what we can get out of the diagram itself, some of the sort of key parameters. And so let's start with what it actually represents. And so a ternary phase diagram, if you're thinking of a binary system, right, we had a composition line on the x-axis, right? We had components A and B. So effectively we had this line down here. Well, now we have a ternary system. And so how we can choose to represent that is with a triangle, right? So we have A and B, but we also have a third component, C. And so we form a triangle here on the base that represents our composition. And so in this case, we're using an equilateral triangle. There are others that use a right angle triangle, but this is not. The ones that are in materials are typically equilateral triangles. And so we also have temperature, right? And so in this case, temperature would be the z-axis. And so basically everything that you can think about in terms of a ternary phase diagram, the dimensionality goes up by 1, right? So this is now 3-dimensional, whereas a binary system was 2-dimensional. And so this is kind of a representation of a eutectic phase diagram in the ternary space. So again, it's a 3-dimensional thing, which is kind of hard to represent on a piece of paper like this. But one thing you'll sort of notice is that there's this sort of big surface that flows down towards the middle, and the same thing over here, and the same thing here. And it all flows down to this point right here. So this low melting point temperature known as a eutectic. Right? All the end member components A, B, and C have higher melting points. So that's the classic hallmarks of a eutectic system. So we're looking at a 3-dimensional space here. And so instead of, so the liquidus, the line in binary that separated 100% liquid from solid is now a surface. So this area that we see up here where the where the arrow is, this area here, and this area right here, these are all examples of liquidus surfaces. So up here, this is 100% liquid, and then when we cross this surface, we're now going to have some solid. And so our liquidus line in binary has now become a liquidus surface in ternary. So everything increases by 1. All right, so instead of showing this 3-dimensional ternary diagram, which is pretty hard to do, typically you're going to see these represented in one of a couple ways. But for the most part, you're going to see it represented like we have here, where we have a 2-dimensional representation. So we're looking at the equilateral triangle of composition. And instead of representing that z-axis, we represent that with contour lines, just like you would see on a topographic map, right? So a topographic map shows the elevation of a region. So this one is Masterson Station Park, and those lines show you the height in the z-axis, without actually having to show you it in 3-dimensional space, right? Same thing here. These lines on this diagram show you isotherms, so constant temperature lines of that liquidus surface. So if I go back, it's basically showing you the contours of these liquidus surfaces that we have, right? That's what it's showing you. Those contour lines of temperature are equivalent to elevation in the topographic map. And that's really what this is showing. So you are often going to see a ternary phase diagram that has these temperature contours, and again, it's representing the liquidus surface. So that's what these lines are representing. And so in this case, it's very similar to the 3-dimensional one we saw, because it's a eutectic where everything is flowing down towards the eutectic point. All right, and again, these temperature contours are of constant temperature. That's one thing to keep in mind. So we're drawing a contour at a fixed temperature. So, for example, 1,000 or 900 degrees Celsius, we're going to have a contour. So this could example be one for 1,000. This could be 900, 800, 700, and so forth until we get down to lower temperatures. So all you're seeing here on this projection then is the liquidous surface. So that's important to keep in mind that that's what that's showing you. All right. So the next thing I want to look at, so now that we've got sort of an idea of what these things look like, one of the first things that you're always going to want to do with a phase diagram is be able to read and write compositions, right? If I put a point on the plot, I want you to be able to tell me what that composition is. Just like if you had a point on a binary system, you should be able to tell me, that is 40% A, 60% B. Same thing here, but now it's going to be a little bit more complex because we have 3 components. And so this just walks you through how we actually obtain and read the composition. And we do so with constructing these parallel lines. So you see A, B, and C, all these parallel lines to the side of the plot. So we're going to start with a point here, right, in the middle. This is the point that we are interested in finding out the composition. So what we're going to do is, starting with that point, we're going to draw 3 lines. And these lines are going to be parallel to each side of the triangle. So I'll have one line A, that's parallel to this base, and we're calling it A because it's opposite of the component A. Same thing with B. I'll draw a line opposite B, and then parallel to the base opposite of that. And then same thing for C. I'm going to create a line opposite the point C, parallel to the base over here. All right, and then we read the compositions from the axes. So from there, where it intersects, we're going to read the different compositions. So where line A intersects the percent A line over here, we're going to read that right here. So this intersects at about 27% A. So that tells us we have 27% A at that composition. If we look at B, and we look at where that intersects the percent B line, we see that it's 46% B down here. And the same thing, if we look at C and look at where that intersects the percent C over here, we'll see that that's 27. So again, this is how we can get composition. And one quick check you should always do is to add these together, right? If I add 27 plus 27 plus 46, do I get approximately 100? And so oftentimes with how precise your measurements are, you might get plus or minus 1 or even 2, but it should definitely be close to 100, close as possible. All right, so I want you to take a look and work on this example. And so normally I'd have you do this on a piece of paper. You are welcome to print this out and try it. But also, you can try to do this in PowerPoint or using some software as well. But I want you to take the composition point A and see if you can find what the composition of that point is using this plot. So stop here and see if you can determine what the composition is. All right, so we're back. So I'm going to go through an example of how to find this composition. So I'm going to X out of the presentation right now, and I'm going to go to another slide I have ready, and we'll just kind of walk through this, and I'm going to do this in PowerPoint so you can kind of see how this works. But for me, I'm just going to use lines in PowerPoint. So I'm going to go up to Shapes and click Line. And again, what I want to do, going back to the instructions, is I want to create 3 lines parallel to the bases. So I have X, Y, and Z. I'm going to start with X and make a line parallel to the base opposite of that. So basically a line parallel to this. And so for me, why don't I just do this? I'll just make a line that traces that axis, so I know it's parallel. And so then what I'm going to do is I'm just going to move it, and I'm going to have that go through point A. Right? All right, so that's my first line. So I'll do it again. So create another line. So go back to insert, shape, line. And then now let's do Y. And so the base opposite of Y is going to be this XZ axis. So I'll do that. And then again, the easiest way I've found to do this is to move it so that it's through A. So it's right on that line. All right. And then I've got one more, and I'm just going to copy and paste it this time. So now I want to look at Z, and the base opposite of that is X, Y. So I'll make my line parallel to that. And I'll go through that point again. All right, so now I've got my 3 lines, and I'm going to read off the compositions. So my first line was parallel to this base, which was line X, so this one right here. And so if I look at the weight percent X line, and I look at where it intersects that line, it looks like it's at 45, right? So let me just write that on this plot for you so you can see it. So this is line X, and so that means the amount of X I have is 45. Or sorry, I'm reading that wrong. So that's a good example here. So it's weight percent X, but as you can see, it starts at 100 and goes back to 0. So this is actually 35. So, you know, I'm doing this in real time, so you're seeing the results of that. So this is 35 weight percent X. All right, so that tells me how much X I have. So now let's go to the next one. So I want to go look at Y. And so Y is here, the base was here, this is the line parallel to it. So this is line Y. And if I look at the axis with weight percent Y, which is over here, I see that it was right on that line that represents 50%. So I had 50% Y. So I'll change that so you can see it here. All right, so now I've got 35 weight percent X, 50% weight percent Y, and so you can probably imagine how much Z I have, but let's go through that as an example. So the last one, so I'm looking at Z here, the line parallel to that is this one going through A, and then this axis over here is the weight percent Z. And so if I look at that, you can see that that intersection is at about 15. And so I have, this is line Z, and I have 15 weight percent, and this is component Z, right? So overall, I have 35 weight percent X, 50 weight percent Y, and 15 weight percent Z, right? And so if you add those up, you got 35 plus 50, that's 85, and then the additional 15, so that equals 100, so that looks good. So if you're doing this on a piece of paper or so forth, again, those numbers might vary because of the, you know, the gradation here, so it might be a little harder to get the exact number, but you should be close to 100% when you calculate these compositions.